Okay, hello folks. Welcome back everyone. Is the mic good? Is the mic working? Okay, so yeah, welcome back everyone. I just wanted to make an announcement to the effect that the new assignment is up. Okay, so yeah, so there's no video this week. I was at the lake kayaking and I didn't have time to make any videos. So no video, no survey, etc. But homework 2 is available. Okay, so homework 1 is due in tutorial this week. So some people have probably already handed in their assignments. And then homework 2 is available here. Okay, I just put the due date on this one to make it a little bit more clear. So there's some graphs, you know, all sorts of stuff to do. Okay, so that's available on the course page. Are there any questions or thoughts? Okay, everyone's all right with that? Yeah, so please get a copy of the new assignment and hand in your homework 1 in tutorial. Okay, sweet. Whoop. Yeah, okay, let's try that. Okay, so what are we up to? So one thing I just, as a bit of a warning, I want to say that this week is going to feel a fair bit more proofy, or proofful, than the last 2 weeks. So we're going to be doing a little bit of geometry. There's going to be a little bit more sort of proofs and mathematical heavy lifting. Okay, so last week we gave a formula for the dot product. Right, so if we have two vectors, when we take their dot product, we take the transpose of the first one and we multiply it like a matrix against the second one. Okay, our other sort of important fact about dot products is that the dot product of a vector with itself winds up giving us the length squared. Okay, so this is very much like Pythagoras. Right, when we have a vector and dot it with itself, we get x squared plus y squared plus z squared. Okay, so the dot product keeps track of length for us somehow. Okay, so those are sort of the basis of our understanding of vectors in geometry. Okay, and we can use vector methods to prove some nice theorems in geometry. Okay, so suppose that we've got these two vectors and they span a parallelogram. Okay, so we've got this parallelogram in space. Okay, so our hypothesis is that if these guys have the same length, then okay, so this is the kind of theorem that Euclid could have proved. Euclid probably did prove, but we're going to prove it using vector methods. So if these two things have the same length, then the diagonals of the parallelogram are at right angles to each other. Okay, so with this kind of statement, we have to think about what it means for a moment. And with a lot of statements in geometry, it's very, very, very helpful to draw the diagram first. So to draw the diagram and see what it's saying. Okay, so we want to draw a diagram which illustrates the geometry. So we're going to do things in the plane. We'll say that this is A. This is B. Okay, now we span this parallelogram generated by these guys. Okay, and the statement is that the diagonals of this guy are at right angles. Okay, so that's our claim. So let's try and prove that using these vector methods. Okay, so instead of using ruler and compass constructions or whatever, we'll use what we know about length and dot products. Okay, so the first key observation is that these diagonals have nice formulas in terms of the vectors. So this guy here is A plus B. Okay, and then this guy here is A minus B. Okay, so what we want to do is check a statement about some vectors that we have nice algebraic formulas for. Okay, so we claim that if these lengths are equal, then the dot product must be 0. Okay? Right, so this is our way of saying orthogonal. Right. Orthogonal or at a right angle. Okay. Any questions so far or thoughts about the setup? Okay, so we've got this thing set up. Now we're going to take the dot product and see what we get. So we have this dot product here. And we can sort of expand it out term by term. Okay, the reason why we're allowed to do this expansion, right? Why can we, break up these plus signs and all this stuff? The reason we can do this expansion is that the dot product works just like real numbers. It works in each entry, just like multiplication. Yep?
It's minus b dot b.
Ah, it is minus b dot b. Yes. Good typo check. Okay, sweet. So we're here. These guys are going to cancel out, so we get this, right? So these cross terms here, they go away. These guys are equal. Okay, so we wind up getting 0 in the end. Okay, so if the vectors have the same length, then the diagonals meet at a right angle. Okay, any thoughts or questions there? Okay, so the idea is that this geometry of the dot product can be sometimes helpful. I just want to write down some of the algebraic facts that we use there. Okay, if we've got one vector dotted against two vectors, then we can do this. Okay, if we've got a constant, we can pull that out of the dot product. And we can switch the order of two terms. Okay, so these are, I guess, an exercise to check. Okay, so to check these, you'd write down the vectors in coordinates and go through like that. Okay, so that's a little bit about using vectors to do geometry. Our next topic is where things get very, very, very proofy. So I want to take the next one a little bit slowly. Okay. So our next topic is limits. And limits in multivariable calculus are a fair bit more subtle than in the real numbers. In the real numbers, there's essentially only two directions of approach. You either approach via numbers bigger than c, or you approach via numbers less than c. Right? There's really nowhere else to go in the real numbers. In every other dimension, though, there's a lot of directions of approach. Right? For a fixed point, we can come at it from many, many, many distinct angles. Okay, so in computing limits in multivariable stuff, we have to be a fair bit more careful. Okay, so what's our definition? Okay, so here, when we do limits, we've got one vector approaching another vector. So the limit as x goes to y is going to be z if okay. And now for folks who took A31, this will be a very familiar definition. If for all numbers bigger than epsilon, bigger than 0, Okay, so what's this saying? This is saying that for any amount of error we want, for any epsilon that we want, there is a difference, delta, such that if the difference between x and y is less than delta, then the error of our function to its limiting value, oh, hey, thank you, doing the good work, is less than epsilon. Okay, so this is our definition of a limit in multiple dimensions. So it's a very abstract definition. I want to do a one-dimensional example and then do a multi-dimensional example. Okay, so our one-dimensional example goes something like this. Okay, so if we're doing things just in one dimension, we'll have some setup like this. Okay, as x goes to 2, 5x, we want that to go to 10. Okay, so what do we need according to this definition? We need to fix an amount of error. So fix epsilon to be bigger than 0. Okay, and now we have to produce an amount of difference so that the following thing holds. Okay. So our goal is to find a delta so that this happens, so that if x is closer to 2 than delta, then 5x is close to 10. Okay, so what we do is we observe this 5x we can factor out. Okay, and now we've got something that looks a great deal like x minus 2. Okay, so this term we can control. Okay. So the way that we get this estimate is we're going to pick delta to be less than epsilon over 5. What happens then? Okay. If we've got that this thing's less than delta, which is less than epsilon over 5, then we get this, which is the conclusion we want. So thus, we get the limit that we wanted. Okay. Are there questions about where that choice of delta comes from? Right? Why do we say delta is less than epsilon over 5? Yeah, sure, yeah.
Previous course we did delta
Yeah, sure, delta equals 2 is also fine. Yeah, if you do this, this will also work just fine. Yeah. So all the math will go through just fine. Are there any other questions or thoughts? Okay, just for a show of hands, who's this the first delta epsilon argument for? Is this familiar? Okay, so this is new to some people. Okay, these are tricky arguments, so we're going to do a couple of them. I'll just make that comment. But this is also fine. Okay, so I just want to write down this comment precisely about errors and differences. Okay. Okay, so to kind of put it informally, f of x gets close to z as x gets close to y. And now the place where we use these epsilons and deltas okay, this is epsilon close. And this is delta close. Okay, so when x gets delta close to y, f of x gets epsilon close to z. Okay, so it's a notion of approximation. Okay, so let's see an example in several variables now. Okay, so now we have to check that when this guy gets close to this guy here gets close to this. Okay, so let's see how this works. We're going to fix some epsilon, and then we will pick delta less than epsilon over k. For some k that we're going to choose later. Okay, so we'll just work with k until we know what correct value to pick. Okay. So now we're going to introduce a key move in this kind of argument. So if okay, so this is a very, very key move in making these kinds of estimates. So what's going on here? The idea is something like this. So if we focus our attention on this point 1, 2, and we say that we're within delta of that point, then we live in some ball of radius delta. Yeah? So our distance from this point to the outside of the ball is at most delta. But we can also think of that as saying that we are between 1 minus delta, or sorry, two minus delta and 2 plus delta. Okay, we can think of this as saying that we live in a particular box. Okay, so oftentimes when you're doing these kinds of limit calculations, or limit proofs, I guess, it's helpful to think in terms of the box instead. Okay, so to go from a circle about your point to a box about your point. Okay, so here's what we've got. Yeah, okay, so circle in box. Okay, it's often helpful to go from this condition, which gives you a circle, to these two conditions, which give you a box. Okay, so what are we going to do with these guys? Okay, yes, sure.
What if you're in the box but not in the circle, like if you're in the corner?
Right, yes, yeah, what if you're over here, right? Yeah, that's very key. The important implication is all of the circle, everything that satisfies this condition lives in the circle. And all of those points then live in the box. Okay? So how can I write this? Yeah, I guess we've written it here. If you're contained in the circle, then you're contained in the box. Okay, very good. Very good. Okay, this last condition is equivalent to this. And now this is the kind of thing that we can do some algebra on. We can do a little bit of algebra here and get things looking more and more like our goal function. Okay? Okay, so what do we do? Okay, so we multiply through by the coefficient that we want on x. we multiply through by the coefficient that we want on y, and we get we can add these two things. And then this is equivalent to the following. Okay, so if we can manipulate this delta, then we can get our limit calculation to happen. Oops. Okay. So our final goal is to get that this is less than epsilon. Right? So what we should pick is we should pick delta to be less than epsilon over 5 again. Okay? So we will pick so we'll pick k in this way. Okay, so what do we get? Okay, so this is the sort of the final draft of our proof. If epsilon is bigger than 0 and delta is less than epsilon over 5, then whenever this point is delta close to this point, our function is epsilon close to 8. So thus, so sort of the key move, and the move that I think will be most helpful coming out of this, is this replacing a circular bound with this box bound. Okay. Good. I think we've got time for one more example of this technique. Questions or thoughts so far? Okay, so one more example of this technique. okay, is this kind of limit here. So here we've got a function and it's not clear how to control things. With these questions, it's often helpful to think in terms of distance. Okay? Oftentimes, if you see some squareds kicking around, it's helpful to think in terms of distance. Okay. So we're going to observe the following. Okay, we can make this function bigger by adding some positive terms. Right, we add on this y squared. And we get this. Okay, so the function that we've started off with is always going to be smaller than distance. Okay, so when this point gets close to 0, our function has no choice but to also get close to 0. So let's try and make that into a delta epsilon argument. Okay, so here we know our function is no bigger than delta. So we're going to pick delta to be equal to epsilon. Okay. So this is sort of our key move. If this thing is less than delta, and we've picked delta to be equal to epsilon, then the distance is less than epsilon. Okay, so now let's use that to control our function. Okay, our function minus its limiting value, well, its limiting value is 0. So we just get our function. Okay, so the thing that we wanted to control is always less than distance, which is less than epsilon. So thus, we get the limit we're looking for. Okay, so these arguments are quite difficult and require a fair bit of practice. To practice them, I highly recommend reading some of the examples from section 2.2. Okay. To get a feel for this kind of argument, you really have to see a bunch of different examples of it. Okay. Any thoughts or questions there? Okay. We're going to come back to these on Thursday because we've seen this one technique of bounding with a box. Oh, okay, everyone's getting ready to go. We've seen this one technique of bounding by distance. For people who are very keen to get started on the homework, I just want to say just a couple last words, okay? Okay, so for the folks who really want to start on homework 2 tonight, there's one little piece of the puzzle we're missing. So I just want to introduce that before the end of lecture. Okay, and this is the notion of contour plots. Okay. Okay, so we've talked about how graphing things in 3D is hard, right? So graphing okay, it's very hard to graph functions in 3D. So one technique that we can use to understand 3D graphs is the following. Okay, so to understand a function with 2 inputs and 1 output, we create something that we call a contour plot. Okay, so what is a contour plot? Okay, a contour plot for the function f of xy is a graph in the plane of the following sets. Okay, so we call S sub k the set of all inputs where a function outputs k. All right, so we look at the points in the plane where a function would output k. So let's have a look at what that would look like. Okay, so let's suppose that our function is x squared plus y squared. Okay, so we're looking at this guy here. So what are the sets sk? The sets sk look something like this. Okay, so S1 is all of the guys that add up to 1. Okay, and then surrounding that, we'd have S2, which is all of the guys where our function outputs 2. Okay, so now what we see is we can plot this for different values of k, and we can understand our function as a collection of curves in the plane. Okay? Yes, sure. No, so k can be any number you want, any finite number you want. Yes. So there's infinitely many different values of k. Yeah. So if we could put in the set, this is S of 1.5 or something, right? There's infinitely many different values we could plug in. Okay, so what do these correspond to on the graph in 3D of this function? Okay, in 3D, our function looks like a parabola, right? It's this sort of cone. Okay, so it corresponds to cutting our graph along a plane. Okay, so when we cut along the plane z equals 1, we get here. When we cut along z is equal to 1.5, we get here. And when we cut along z is equal to 2, we get here. Okay, so these SKs correspond to the x and y input that give you something on that plane. Okay, so that's a little bit about what contour plots are, and there's a lot of practice on homework 2. Okay, so next lecture we'll pick back up with this limits business and contour plots.